video, I wanted to go over problem 4-14 and 4-15 from the book, and the reason why is because I didn't have time to go over them in class on Monday. And so just to make sure that, so I have the Elements of Chemical Reaction Engineering, 4th edition by Fogler, and so if you have Essentials of Chemical Reactor Engineering, I'm not sure which problems those correspond to, but they should be in that book too, so you can just look them up based on the problem. Like, so anyway, for number 14, so this is 4-14, you have 2,500 gallons per hour of metaxylene, and it's isomerized to a mix of metaxylene, orthoxylene, and paraxylene in a reactor with 1,000 cubic feet of catalyst. So basically you have 2,500 gallons per hour of metaxylene, and it's isomerized to orthoxylene and paraxylene. And the reactor, so the volume of the reactor is 1,000. Actually, sorry, this is the weight of the catalyst. No, that's the volume. Well, oh, actually, it's the volume of the catalyst. So it says you have 1,000 cubic feet of catalyst. And the temperature is 750 degrees F, and the pressure is 300 psi gauge. And with these conditions, you get that the conversion is 0.37. So then if you change your flow rate from 2,500 gallons per hour to 1,667 gallons per hour, then X is equal to 0.5 with the same conditions, so same temperature and pressure. And so then the question is, it says a second plant is proposed that needs to process 5,500 gallons per hour of metaxylene at the same temperature and pressure, so you need 5,500 gallons per hour of metaxylene at same temperature and pressure. So it says what size of reactor, in other words the volume of catalyst, do you need to get a conversion of 46% instead of 37%. So what size reactor to get X is equal to 0.46 with this flow rate? So the first thing we want to do with this problem is write down the reactions, because it didn't really give the reactions, it just described them. So first of all, I'm going to do that. So reactions, so metaxylene to paraxylene, and I'm just going to say that's K1, and you have metaxylene to orthoxylene, and I'm just going to say that's K2. And you could also have orthoxylene to paraxylene, but I'm going to neglect that. I'm just going to say that's really small compared to these two. And So then the next thing you would do, like normally for this problem you would just jump into the mole balance and start going through it, but in this case we don't know what type of reactor we have. I mean, it could be a CSTR or it could be a PFR. We need to figure out what the reactor is so then we can get our rate constants and other information from this information that we already have. So I'm going to erase some stuff real quick, and then I want to start with a CSTR. So basically I'm going to assume that it's a CSTR and go through that and show you how you would know if it were a CSTR or not. I'm going to write down what we know here too. So basically we're figuring out the type of reactor. First of all, we know that when V naught is equal to 2,500 gallons per hour, X is equal to 0.37, and when V naught is equal to 1667 gallons per hour, X is equal to 0.5. So then coming over here, first I'm going to say that we're assuming it's a CSTR. So then we want to do a mole balance. And the mole balance for CSTR is V is equal to FA naught X over minus RA. And then for the rate law, we need to do a net rate law because we have two reactions. So this would be minus Rm is equal to K1 Cm plus K2 Cm. And then we can just say that this is equal to K Cm, and we can say that K is equal to K1 plus K2. And this is something I would definitely review for the exam on Friday if you're unsure about how to do the net rate laws. Like say you have either series or in this case parallel reactions. Make sure you know how to do the net rate law. So then we need to know what Cm is, so get that from the stoichiometry. So Cm is equal to Cm naught 1 minus x. And then we can combine these. So V is equal to, and so I'm just going to say Fa naught is Cm naught V naught over x, and this is over K Cm naught 1 minus x. So then that cancels, and so this is equal to V naught x over K 1 minus x. So then we can multiply the K over, and we can say that Kv is equal to x over 1 minus x, and that's multiplied by V naught. So then we know that the rate, so if the volume doesn't change between these two reactors, or between these two reactions, and the rate constant should also be the same. So we know that Kv should be the same for both cases. So then what you can do is plug in for the first one, plug in V naught and the conversion, and then do the same thing for the second, and see if they're equal. And if they are, then you know that this is a CSTR, and if they're not, then you know it's not. So for case 1, we have that Kv is equal to x is 0.37 multiplied by 2,500 over 1 minus 0.37, and that's equal to 1468 gallons per hour. And then for number 2, we have that Kv is equal to 0.5 multiplied by 1667 over 1 minus 0.5, and that's equal to 1667 gallons per hour. So we know it's not a CSTR because these aren't equal. So then the next step for this is to assume, okay, well, it's not a CSTR, so it's probably a PFR. So I'm going to So you go through the same sort of process to see if it's a PFR. So I'm going to erase this and then do that. So now we're assuming a PFR. So assume PFR. And so the first thing we want to do is a mole balance. And so V is equal to Fm naught 0 to x dx over minus Ra. So the rate and stoichiometry are still the same for this, so I'm just going to skip straight to the combined step. So basically if you plug in the rate that we already had and then the Cm naught, V naught for Fm naught, then you have V is equal to Cm naught, V naught, 0 to x dx over k Cm naught 1 minus x. So then this can cancel, and so then we have V naught over k 0 to x dx over 1 minus x. So then V is equal to V naught over k natural log 1 over 1 minus x. So then we can multiply the k over. So you have Vk is equal to V naught natural log 1 over 1 minus x. So then we can do the same thing because V and k should be the same in this, for this case too. Volume multiplied by the rate constant should be the same for both cases. So for number 1, we have that Vk is equal to V naught, which is 2500, multiplied by a natural log 1 over 1 minus 0.37, and that's equal to 1155 gallons per hour. And then for number 2, we have Vk is equal to 1667 multiplied by a natural log 1 over 1 minus 0.5, and that's also equal to 1155 gallons per hour. So we know that it's a PFR. So then what we can do is, so the question was what you want, so you have this new plant and you want a V naught of 5,500 gallons per hour and you want a conversion of 46%. So then what does your volume need to be? So the first thing you can do is calculate K, and we know that Vk is equal to 1155, and we know what V is because it was given as 1,000, so we know that K is equal to 1155 over 1,000. So that's equal to 1.155. And then we can just plug these straight back into this equation we already derived, and so we have V is equal to V naught over K, so V naught is 5,500. K is 1.155 multiplied by a natural log of 1 over 1 minus 0.46, and that's equal to 2934 cubic feet of catalyst. For number 15, and I'll actually just read this problem. So it says, it is desired to carry out the gaseous reaction A to B in an existing tubular reactor consisting of 50 parallel tubes 40 feet long with a 0.75 inch inside diameter. Bench scale experiments have given the reaction rate constant for the first order reaction as, and then it gives the reaction rate at 200, or the reaction rate constant at 200 degrees F and 300 degrees F. At what temperature should the reactor be operated to give a conversion of A of 80% with a feed rate of 500 pound-m per hour of pure A and an operating pressure of 100 psi gauge. A has a molecular weight of 73. Departure from perfect gas behavior may be neglected, so you're assuming ideal gas. And the reverse reaction is insignificant at these conditions. So this is 4-15. So you have a gas phase, that's A to B, and you have an existing tubular reactor with 50 tubes, and the length is 40 feet. The inner diameter of each tube is 0.75 inch. And then the measured reaction rate constants were K is equal to 0.00152 second minus 1 at 200 degrees F, and K is equal to 0.0740 second minus 1 at 300 degrees F. So, and then they want to know the temperature that you should operate the reactor at to get X is equal to 0.8. And then it also gives FA naught is equal to 500 pound-m per hour. P is equal to 100 psi gauge. The molecular weight of A is 73, and you have ideal gas. So the first thing we want to do is find the volume of the reactor, and so that's pretty easy. Basically, you just say the volume is equal to, so you know the volume of the tubes, and you know you have 50. So it's the number of tubes multiplied by the volume of each tube. Oops. So that's equal to, you have 50 pi, and then the diameter is 0.75 inch, but you want that in feet, so 0.75 divided by 12 squared, multiplied by the length, which is 40 feet, over 4. And this is equal to 6.14 foot cubed. And then, actually, this isn't FA naught, this is the mass flow rate. So then we want to find FA naught, and FA naught is the mass flow rate divided by the molecular weight. So 500, so this is pound per hour. So 500 pound per hour divided by 73 pound per pound mole, and that's equal to 6.86 pound mole per hour. So mole balance And so this is a tubular reactor, so PFR. V is equal to FA naught 0 to x dx over minus RA. And then for the rate, I'm just going to assume that it's elementary, so minus RA is equal to K CA. Next is the stoichiometry, and this is gas, so CA is equal to CA naught 1 minus x over 1 plus epsilon x, and epsilon is 0, so this is Ca naught 1 minus x. So then we want to combine everything, and so we have v is equal to Fa naught 0 to x dx over minus Ra is equal to Fa naught 0 to x dx over k Ca naught 1 minus x. And I'm going to pull the k Ca naught out, so then I have this is equal to Fa naught over k Ca naught, and then I'm just going to integrate that, so natural log 1 over 1 minus x. And then we can calculate Ca naught from the ideal gas law, so Ca naught is equal to Ya naught P over RT. And then I'm going to actually just plug this straight into that equation. So doing that, I get that V is equal to Fa naught RT over K Ya naught P natural log 1 over 1 minus x. So now we want to solve this equation for K, and so K is equal to Fa naught RT over V Ya naught P natural log 1 over 1 minus x. And the reason why we want to solve this for K is because we also can get an expression for K from the Arrhenius equation. And so then we can set that K equal to this K, and then we can solve for T. So I'm going to erase some stuff real quick. So I'm just going to rewrite this equation that we just derived for K. So K is equal to Fa naught RT over V Ya naught P natural log 1 over 1 minus x. And then we know that K is also equal to K1, so K is equal to K1 multiplied by the exponent of E over R 1 over T1 minus 1 over T. And so then we can just set these equal. And so once we set these equal, we can solve for T. But the one issue is we don't know what E is. So we can solve for that though, because we know what K is at 2 different temperatures. So what we can do is just say that we can basically just take this equation and say, okay, K at this K is 0.00152 is equal to, and then this one 0.0740 multiplied by the exponent of E over R, and then 1 over, and then this first one would be the temperature at this. So, actually, is that right? No, this temperature here would be the temperature at this one. So this 300 F, which is 759.7 Rankine, minus 1 over, and then 200 F is 659.7 Rankine. So then if you solve for E over R, you get 19,500 R. So then you can plug this into here. So we're setting these two equations equal, so I'm just going to write that. So this is equal to K1 exponent E over R 1 over T1 minus 1 over T. And then we should have everything, so FA naught. So we solved for FA naught, it was 6.86 pound mole per hour. R should be 10.73 for the correct units. Let's see. T. So we're solving for T. The volume is, the volume is 6.14 foot cubed. We solve for that. YA naught is 1. And this foot cubed, oh, never mind. So P is 114.7 PSIA, because remember it was given to us in gauge, so we need to add 14.7 to it. And we know X is 0.8. It doesn't matter what K you use, just make sure you use the right corresponding temperature. So I used 0.00152. But then this is in seconds, and our stuff over here is in hours, so we need to convert this to hours. So I multiplied this by 3,600 seconds over 1 hour. And if you go through and write in all the units, you'll see why you have to convert that. And so then E over R, this was 19,500 R. And then this temperature, the temperature that corresponds with this one was 659.7 R, and then 1 over T. So then if you put all this in and solve for T, you get that T is equal to 738 R, which is equal to 278 degrees F.